again, I found this very interesting, and I want to share it with everybody who might have an interest with this. It has to do with time delays. And in the book, I'm reading for, a long time, and, you see examples for time delays in assembly and in C. And you just take them for granted, they explain you the math and what have you, and take it for granted running, and you think it's running like at what you program it for, like, 1 millisecond or whatever. It ain't so. I mean, don't ever trust the book. The books. If you're diligent, you catch more errors in books than anything else. Here's an experiment. I have 5 different ways of the delays to measure the delays that are supposedly correct per the book. We can consider them bullets or missiles or whatever. We'll start with the first one. We'll start with what the book suggests. 922 cycles. This will be a delay. 922 cycles times 1.085 microseconds. This is about 1 millisecond. So, and then here we enter how many milliseconds we want. We want 1 millisecond, okay? So that's the first one. We'll load that one. Forget the other stuff here. I'm just using this one. This cradle thing for the delay things. So let's get a snapshot of what's going on in this one, the Keel version. So here we go. Up here, I'm sorry, I'm doing 3 things at the same time, and let's take a measurement from there to there. Now remember, we said 1 millisecond, right? We set it for 1 millisecond. The book will agree for it. What are we getting? We're getting 5.33 milliseconds right here. 5.33 milliseconds, right? Okay, that's one compiler. So let's do the other compiler. Let's do SDCC, which is a free compiler. I can only go like to 2 kilobytes on the Keel, or pay 1,000, or use the free one here and go as many bytes as I want. So let's try the SDCC. Now here's SDCC. The only thing we changed was the delay thing there. It's in a simulation mode, and I forgot how many milliseconds, but after so many milliseconds, I don't know if you can see that functioning there. After so many milliseconds, it will trigger port 1, pin 0. We're not concerned about that now. This is another compiler, right? Remember, we had 5.33 in Keel. So now let's measure the SDCC compiler. Look at this difference. The SDCC compiler with the same instructions. I don't know if I show you the same instructions. This one is measuring 14 milliseconds, which is 14 thousandths of a second. But thousandths of a second is a lot. So let me show you again to show you that it has the same instructions. 922 cycles times 1.05 microseconds equals 1 milliseconds. This is SDCC, and this is the same thing there. 922, the same loop, same everything. Let me move this over. Oh, it's in simulation mode. So already you pretty much know what's happening. If you don't watch your timing, you're gonna have, erroneous errors in your program if you think your timing is right. So I took it a bit further. I used the internal timers. I used the internal timers, using the timer mode, and these run free of the program. These run free of the code. So let's get timer mode. See, these are different. The delay is done with the timers, and excuse me, in the other examples, the entire program waits till that timing cycles waits for thousands of seconds. The entire program waits for thousands of seconds. Like in this, it doesn't. The program is free to run. So let's run that one and see what we got. We have it loaded. Oops, sorry. Here we go. Here, let's change the frequency so we can get a timing thing. Here's one end, more or less, and here's the other. So here we have 0.02 milliseconds, which is pretty right on. I'm not gonna nitpick about a couple of microseconds. So with the internal timers, it's true to its word. So, okay. Then I went to assembly to see. So already we know we can't trust the timing cycles in different compilers, because each compiler generates its own code and it adds the assembly code as it deems fit. So when using those delay loops, you have to be very careful and tweak them, or use the timer if they're available, if you're not using them for something else. So this is the assembly code. If we can get assembly, that's the timimg. Here's assembly code to just do the delay. And we can even count the cycles. Each instruction takes like machine cycles. In this case, the machine cycle is 1.085 microseconds. So, if you add all the cycles up, then you can really get nitpicky about how many milliseconds of time you're using. So let's test this one, and I'm gonna run it. And here we go. We get a snapshot. And the assembly language, it came out pretty close, 1.12, because I'm not really fine-tuning it. It took a lot of thought and programming this and everything. But I can get it down just by removing some from this function here, or the 255, tweak it to that. But the assembly is good. Now what took me all day was, and it was silly, I embedded the assembly code, into a C function. And it's a simple program. It's just, we just pausing one pin. We're just pausing that pin with the yellow thing. And the other, you haven't seen it yet, is the clock frequency, and I'll show you what's really happening. Those two probes from this little logic analyzer is what we're using, what we're measuring with. So let's remove that one. This is number 5, and this is with the embedded assembly code. Now with embedded assembly code, I think I can suggest right now, if you need timing, critical timing, use the timers, or I see something strange here. I don't know if I programmed it. I see something strange in, maybe I didn't program it right. It's really, we might not get a reading in this, but so far you get the general idea. Let's see if we get anything. No, this one is I didn't program it right. Can't do it right now. But let's make sure the pins are in and everything. Something didn't program right on that one. It functioned. I might have copied the wrong code for it. So Um, like as I was saying, for timing, I would not ever trust the loops, the delay loops as we saw earlier. Like this thing here, which are very very common. They're very very common. But use either the timers or embedded assembly in the C code, if at all possible. So that's about all I wanted to share. And I found it very interesting. I had no idea. I had no idea that it was so off. I was expecting a few microseconds and things like this. But it is like, wow. It's from 1 millisecond to 15 milliseconds. Or like a 10 millisecond difference. This is the other chip. Yeah, the thing I'm playing with. So 5 chips later and a few programs. Now we know. Don't trust the delay loops because the the compiler generates as much assembly code as it needs, and we already saw that each assembly instruction takes a little bit of time, like 2 machine cycles. Like just this little program on the top is 1, 2, 3, 4, 5, 10 machine cycles. It's almost a millisecond. Well, 10 machine cycles. It's like 10 microseconds. 10.85 microseconds off. And that's not a lot. And a millions of seconds ain't much, but when you're doing them millions of times, they really do add up. So that was my pet peeve. Actually, I really enjoyed bumping into this and taking measurements with this. Oh, what I was going to show you. This is down here is the clock. Right here is the frequency. I need to calibrate the voltage. But there's the frequency on the pin. I know that pin there. I'm sorry. And so this thing is pretty versatile. It has a lot of different things. Anyhow, I hope you enjoyed this little video. I don't know what to call it. Warning about life cycles, or finding book errors, or I don't know. Anyhow, I hope you enjoyed the video, and I'm signing off before this music gets to me. Over and out. Bye.